All right, open up your book to section 4-5. We're on page 211 in your book. The title of this section is Rational Functions, Asymptotes, and Discontinuities, and the objective is to discover some properties of polynomial and rational algebraic functions and their graphs. Okay, so let's go back and refresh our memory a little bit with rational numbers. A rational number, if you recall, is a number that can be written in the form of an integer divided by an integer. And there's actually several different ways that we can write these fractions. We can have what's called a proper fraction if the numerator is less than the denominator. So if something like 3/4, 3 is less than 4, so that's a proper fraction. We can have an improper fraction when the numerator is equal to or greater than the denominator. So for example, 4/4 is an improper fraction because the numerator equals the denominator. Or 7/4 is improper because 7 is greater than 4. And then finally, we can take and rewrite these improper fractions as a mixed number. If you go through and divide, you'll find, for example, the 7/4 turns out to be 1 3/4 when I divide that. That is, you write it as a whole number out front with a fraction after that, and that fraction is going to be a proper fraction. That's a mixed number. So that's what we know from rational numbers, and let's see how that applies to then rational functions, which was what this whole section is about. We're going to talk about what's called a rational algebraic fraction. I'm going to abbreviate that RAF just because we've got several times that we'll refer to this, so I'm going to use RAF for that acronym for it. But a rational algebraic fraction, we're going to let f of x be a rational function. So that means it can be written in the form of n of x divided by d of x. That's what we defined in the first part of this as a rational function, or rational algebraic function. So we can end up with a proper rational algebraic fraction if the degree of the numerator, n of x, is less than the degree of the denominator, d of x. We call that a proper rational algebraic fraction. Likewise, we can have an improper rational algebraic fraction if the degree of the numerator, n of x, is greater than or equal to the degree of the denominator, d of x. And again, this idea of proper fraction and improper fraction comes directly from what we know about rational numbers with our examples that we started with on this slide. And then it turns out you can simplify an improper rational algebraic fraction and get what's called a mixed rational algebraic fraction. And a mixed rational algebraic fraction is a rational function that's in this form. You've simplified it to rewrite it as f of x is equal to some quotient, q of x. That's going to be a polynomial, but it's q of x plus, and then it's some remainder, so we'll call that r of x over d of x. If you can take your rational function and write it in this form, it's now a mixed rational algebraic fraction. A couple of things here about the functions we're defining here. Q of x, r of x, and d of x all have to be polynomials when you get done with this. And the quotient r of x over d of x is a proper rational algebraic fraction. If you end up with this, then this is what we call a mixed rational algebraic fraction. A couple of notes here. If you're trying to convert between these two, then you can use synthetic division or long division in order to convert from a improper rational algebraic fraction to a mixed rational algebraic fraction. The goal here is we're trying to get that to be a proper fraction, or to involve a proper fraction. So if it's improper, we'll use division to help us get that fractional part as being a proper fraction. Okay, so let's take a look at example number 4 there on page 217 in your book. They give us a function and they ask us to plot this. Now they just ask us to plot it. We're going to go through and come up with all the key features of this function. In fact, we're going to start out with long division to simplify this function f of x. So let's write down what f of x is equal to. F of x is equal to 3x squared minus 25x minus 50, and that's divided by x squared minus 16x plus 60. All right, so let's use long division to simplify this. So long division looks something like this. It gets set up a little bit different than synthetic division. We'll take the denominator, which is the x squared minus 16x plus 60, and we're going to write that out front. And then we put our division bar here. We're going to divide that by the numerator, which goes underneath this division bar here. It's 3x squared minus 25x minus 50. Now to divide this, what I'm looking for is what do I need to multiply this x squared out front by in order to end up with a 3x squared? Or another way of saying that is to take the 3x squared that's under that division bar and divide it by the x squared to figure out what that number needs to be. And clearly in this case that's going to be 3. So since 3 is just a constant, I'm going to put it above the constant of 50 over here. Technically you don't have to worry about lining things up, but I like to line things up properly there. And now what I do is I take that 3 that I just wrote down and I multiply it by this polynomial that I have out front. So 3 times the x squared would give me a 3x squared, and I'm going to write this down below the polynomial that I have, or the quadratic that I have under my fraction bar. And I'll line up my terms. So this is an x squared term, so I line it up below my x squared. Multiply the 3 times the next term there. 3 times a negative 16 is going to give me a minus 48x. And then finally take the 3 times the 60 is going to give me 180 is what I end up with when I multiply by 3. And then what I need to do is I need to subtract these. So I'm going to put this in parentheses and put a subtraction out front. I'll put a difference bar here so that I can actually find the difference of these two. And then write it down. I put this in parentheses just so you realize that minus sign has to get distributed all the way through this second polynomial that I wrote down. So 3x squared minus 3x squared, those cancel each other out. That's what I'm trying to do. I have a negative 25x, and then I'm minusing a negative 48x. So that turns out to be a plus 48x, and so that turns out to be, what, 23x when I combine those. And then I have a negative 50, and again I'm minusing the 180, so that turns out to be a minus 230, it looks like. All right, so let's rewrite what f of x is equal to. And actually, we're going to rewrite f of x in a couple of forms here. So I have f of x is equal to, actually, I should probably write the remainder of this over here just so we realize what we have here. This part that I end up with, since there's no more x squareds in that, that's my remainder part. So I have 23x minus 230 as my remainder over the quantity I was dividing by, which is x squared minus 16x plus 60. That's my result. That's what I'm going to write down here. So my answer is my quotient was 3. My remainder was the 23x minus 230 divided by x squared minus 16x plus 60. There is long division. That's the process you go through to divide and to simplify this and to get this remainder part as a proper rational algebraic fraction. Notice the degree of the numerator is now less than the degree of the denominator. In fact, I'm going to simplify this here a little bit. It looks like I could factor this, so I'm going to do that. I'm going to write it as 3 plus, it looks like I could factor out a 23 from the numerator and be left with x minus 10. And if I factor the denominator, I need two numbers whose product is 60 and sum is negative 16. So that sounds like 6 and 10 here. X minus 10 and x minus 6. And actually, you'll notice that you have some values here that you could cancel out. You've got an x minus 10 in both the numerator and denominator. You can cancel that out, but you just got to be careful and make sure you indicate the domain. Remember that since x minus 10 is in the denominator, this function is not defined at 10. If I cancel those out and write it as 3 plus 23 over x minus 6. That's fine to do, but I need to indicate that 10 is no longer part of this domain, so I need to say that x cannot be equal to 10. I'll squeeze that in there. That's my domain to keep those two the same. Make sure you keep that domain in the problem if you simplify like that. Now the interesting part of this is that these parts now that I have here will be I can use to help me come up with the next two steps in this. So the next step of this is to find my vertical asymptotes. And so when you look at this equation here, either one of these, when you look at either this guy right here, which doesn't have a common factor at the numerator, or when I rewrote it, I can clearly see there's no common factor at the numerator. That turns out to be my vertical asymptote there. Okay? It's a place where the where the denominator is equal to 0, but the numerator is not equal to 0. And so x minus 6, if that's equal to 0, I'm going to be undefined at that point. And so I can solve that to find that x equals 6 is my vertical asymptote. This is my vertical asymptote. I'll just say VA for vertical asymptote. All right. The next part is to find the removable discontinuities. All right, so to find your removable discontinuities, in fact, we want the xy coordinates of our removable discontinuities. And you can do that by going back up to this equation. And let me do this in a different color here. This in red, I guess. That if I look at these guys here that have common factors, those guys right there, I'll call that RD for removable discontinuity. Those guys right there, when I have common factors that would cancel out, or when you look over here at your domain that you've excluded there, those tell me my removable discontinuities. All right, so it turns out that x equals 10 is going to, I guess I should write that down here this way. I should say x minus 10 equals 0. So x is equal to 10 when I solve that is my removable discontinuity. That's how I'm finding that, is by taking that factor as a common factor with the numerator and setting it equal to 0 to solve that. Now, it turns out you can actually find the location of the y value of where that removable discontinuity is. And to do that, you have to take that simplified form that we had here. I'm going to call this y here, which is equal to 3 plus the 23 over x minus 6 was that simplified form. And again, this is on the domain for x not equal to 10. But if you actually plug in 10 in here, it turns out it will give you the actual y value of where this removable discontinuity has to be. So let's do that. This will be 3 plus 23 over 10 minus 6. And what's that end up giving? 10 minus 6 is 4, so that's 3 plus 23 over 4. 23 over 4 is what, a quarter shy of 6, right? 24 over 4 would be 6, yeah. So that's 5 and a quarter, or 5 and 3/4. So 3 plus 5 and 3/4 would be 8 and 3/4. 8.75, we'll say, is our value. So together then, from this, we find that we have a removable discontinuity at x equals 10, y equals 8.75. That is our removable discontinuity. I'll write RD next to that just so I remember that's my removable discontinuity. All right, now let's find our x-intercepts. And you can probably guess what the next thing is going to ask us to do here, but let's find our x-intercepts first. Those are pretty straightforward. We've done that a number of times now. All you got to do is set your equation equal to 0 to do that. I'm going to again take that simplified form that I have there, where I've canceled out the x minus 10s to do this. So it technically would work with either form there. Just a little more work in the other form. Subtract the 3. And then multiply by that x minus 6, you'll have a negative 3x, and then plus 18 equals 23. And then we have to subtract the 18 and divide by 3 here. So x is equal to, subtracting 18 will leave me with 5, divided by a negative 3, it sounds like. You can do that in a couple of steps if you need to, but if you're okay with doing that in one step, that's fine to do as well. And so that tells me then that at x equals -5/3, or what is that? -5/3 would be 1 2/3. I don't know if there's an advantage to writing it that way, but I guess I'll write it in that mixed number form. -1 2/3, comma 0 is my location for my x-intercept, and they wanted it as an xy ordered pair there, so that's why I've written it that way. All right, the next thing to do is to find your y-intercepts. And the y-intercept just simply means you got to plug in 0 into your function, right? So if I take f and I evaluate it at 0, again, I'm going to use that simplified form that I was working with. So that's 3 plus 23 over 0 minus 6. We're plugging in x is 0. And what do we end up with when we do that? We've got 3 plus 23 over a -6. And so 23 over -6 is what? 24 over 6 would be 4, so we're just, 6 shy of 4, so that'd be 5/6 there. So it's 3 minus 3 and 5/6 is what we've got there. Again, that's a -6 in the denominator, so that's, I'm going to change that to subtraction. And so what do we end up with? Just a -5/6, it looks like, is our value there. So that tells me my y-intercept then. My y-intercept, they wanted me to write this as an ordered pair here again. So that would be at x equals 0, y is a -5/6. Just close to -1 is where we're at on the y-axis. All right. And one last thing that we need to do before we try to sketch this thing, which is kind of the goal that they gave us here, or the question they asked us to answer, is to find our horizontal asymptote. And again, once you've simplified this and put this in this mixed number form, or I should say the mixed rational algebraic form, I'll rewrite this as 3 plus 23 over x minus 6 was our equation. And again, it's for x not equal to 10. Don't forget that domain there as you write this down, so that I don't forget that I'm not defined at 10 here. So from this, that 3, the quotient that you have out front, this guy right here, tells me what my horizontal asymptote is. This implies that y equals 3 is my horizontal asymptote. I'll call it HA for short for horizontal asymptote. All right. So now let's put all this together here. And let's see if we can sketch this graph. We need a little bit bigger window here to put this in because of some of the numbers that we're dealing with. And let's just go through these one at a time. Our vertical asymptote, we said, was at x equals 6. So let's mark x equals 6. There's 2, 4. This is a 6 right here. At x equals 6 is our vertical asymptote. We said we had a removal discontinuity at 10. X is 10, so there's 10 and 8.75. So 8.75 would be about halfway between here, it looks like. I'm going to put an open circle there. Maybe I should make that a little bit bigger so it's clear that it's an open circle. Let me do that. So at 10, 8.75. There we go. And we said we had an x-intercept at -1 and 2/3. So there's -2. That's close to -2 here. So let's mark that right about here. Is our x-intercept. We had a y-intercept at 0 and then -5/6. That's about 0 and -1, so that's going to have to be about right here. Those are really close to each other. And then finally, we have a horizontal asymptote. We said at y equals 3. So y equals 3, that's 2, 4. So that's right down the middle of this is where we'd have a horizontal asymptote at. And so now I should have enough information here to sketch this. Again, I can see because of my x and y intercepts that I must start out above the x-axis here, obviously, but I'm below the horizontal asymptote, and I'm going to head towards those 2 points and cross through, and then head down towards this vertical asymptote that I have here. And then over there on the right side, since I already have the hole indicated, I know that I must be sketching above the horizontal asymptote here, so I know where the hole is that I'm headed for, and then I've got to continue on towards a horizontal asymptote there on the right. So there's a pretty good sketch of what this function f of x must look like. All right, let's take a look at another example. Example number 2. They gave us a few steps to go through. I'm going to go through kind of those same steps, but I'm going to do a few other things as well. I'm going to actually take a step back here, and they gave us the equation written in a slightly different form. I'm going to go back to this form right here of, let's suppose that we start out with, again, a problem that looks similar to the last one. We had a quadratic over a quadratic. Negative 2x squared plus 12x minus 15 over x squared minus 6x plus 10. And we're going to go through kind of the same steps here that we just went through on the previous problem. The first thing to do is to simplify this. And we're going to simplify this using long division again. All right, so to use long division, I put the x squared minus 6x plus 10 out front. And my division bar, and then it's the negative 2x squared plus 12x minus 15 underneath that division bar. And again, the question that I'm asking myself here as I go through this long division is, what do I need to multiply x squared by in order to end up with a negative 2x squared? Or better, you could say, take negative 2x squared and divide it by x squared out front to figure out what that number needs to be. That obviously needs to be a negative 2. And since it's just a negative 2 with just a constant, I put it above the constant of negative 15 there. And now multiply that negative 2 by this quadratic that's out front. Negative 2 times x squared is a negative 2x squared. And then negative 2 times 6x is a positive 12x. And then negative 2 times 10 is a minus 20. And again, you have to subtract this. I like putting that in parentheses with a negative out front just so I don't forget to distribute that negative sign all the way through here. Negative 2x squared minus a negative 2x squared, those cancel each other out. That's exactly what I'm trying to do. 12x minus 12x, those cancel each other out. Negative 15 and then minus a negative 20, so that's plus 20. So that'd turn out to be a positive 5 that we'd end up with here. And so we can write that the remainder part of this is 5 divided by that denominator of x squared minus 6x plus 10. So there's what the long division gives us. And let's actually rewrite this then. So we'd end up with f of x is equal to, it's negative 2 plus 5 over x squared minus 6x plus 10. Now this is really close to what the original problem is that they give you in the book, but we're going to rewrite it here in a different way in just a minute. Okay? If you could factor that denominator, I'd say we'd factor it at this point, but I think you're going to find out that you can't factor that. In fact, that leads us to the next question that we have here is, does f of x have any discontinuities? Which should kind of make you wonder here, because we're not saying find the vertical asymptote or find the removal discontinuities like we did in the last problem, but does it have any? Well, if it's going to have any, then that means that denominator has to be equal to 0. And if you try to take x squared minus 6x plus 10 and set it equal to 0, you could try factoring this. Or you could try using quadratic formula. If you use quadratic formula on it, realize you're going to end up with x is equal to the opposite of b. That's 6 plus or minus the square root of a negative 6 squared is 36 minus 4ac, that's minus 40. That's our problem right there. You got the square root of a negative number. This is all over 2a. So in terms of the real numbers, no, there's no solution, but it does have a solution, of course, in the complex numbers, but that's not what we're working on. So it turns out that the answer to this is no. Does it have any discontinuities? No, it does not. That denominator is never equal to 0. That's the only way you're going to end up with a discontinuity. All right, so let's take that denominator then instead, and let's write it in vertex form. That's the d of x, the denominator part of this. So let's see if we can write this in vertex form. And so we've got f of x. Actually, let me just focus on the denominator first. And then we'll go ahead and rewrite the whole function. So we had x squared minus 6x plus 10 is the denominator part of this. So if we want to write it in complex or in vertex form, then the way to do that is by completing the squares. So I'm going to write this as x squared minus 6x. Remember, you associate those two terms together first. And then you have to add a clever form of 0 here in this next step. And the clever form of 0 is determined by this middle term, or this x term here. Take half of it. Half of negative 6 is a negative 3, and square it turns out to be a positive 9. That makes that a perfect square there. And that's plus 10. And then if I add 9 to this problem, I have to make that a clever form of 0. So I have to subtract 9 back out of it. So therefore, I don't change the problem at all. And now what do we end up with here? I have x minus 3 squared. And then 10 minus 9 is going to be plus 1 then, right? So I can rewrite f of x then this way. I can say that f of x is equal to, it's going to be the negative 2 that I had out front, plus 5 divided by, and then it was x minus 3 squared plus 1. Now, it might not seem like an obvious step here, but the fact that we had no discontinuities is what's leading me to this step of writing it in its vertex form. And what's interesting, and that's what the other part of this had to do, was to evaluate f of x at the vertex. So if you look at your vertex here, the 3 there, x minus 3, the x equals 3 is my vertex. So the question is, what is f of 3 equal to? Turns out our resulting graph is going to have a vertex. If I evaluate this at 3, it'll tell me what the corresponding y value is there. So at x equals 3, what's y equal? I'll end up with a negative 2 plus 5 divided by, it's going to be 3 minus 3, of course, squared plus 1. And what does this simplify to? You've got 3 minus 3 squared, that's 0, plus 1, that's 1. So negative 5 plus, negative 2 plus 5 is 3, it looks like, is what we end up with. So we're going to have a vertex at x equals 3, y equals 3. Okay? We'll note that just so we can sketch that in our graph here in just a minute. All right, the next thing is to find your intercepts. What are your x-intercepts and your y-intercepts? So again, we've done this now many times. You just set your equation equal to 0. So you have a negative 2 plus 5. I'm going to go ahead and write this in that vertex form that we have here, I guess. X minus 3 squared plus 1. Move the 2 over to the other side to get you 2 is equal to 5 over x minus 3 squared plus 1. And now move that x minus 3 squared plus 1 over the other side. In fact, I think I'm going to do like kind of a cross multiply here. I'm going to move the 2 over to the right and the x minus 3 squared plus 1 to the left. So I have x minus 3 squared plus 1 equals 5 over 2 is what you'd end up with. Again, multiplying both sides by the x minus 3 squared plus 1 and then dividing both sides by the 2 is what I have there. Okay, don't have quite enough room. Let me scooch this over here then. And now solve that. Subtract 1 from both sides. You've got x minus 3 squared is equal to, what, 3 halves when I subtract 1 from both sides. And then take the square root of both sides. X minus 3 is equal to plus or minus, don't forget a plus or minus there, square root of 3 halves. And then add your 3. So there's our x value. X is equal to 3 plus or minus the square root of 3 halves. And that might not be a value that we recognize here. 3 halves is 1.5, and the square root of that is somewhere around 1.2-ish. So these are approximately, what would that be? If I add 3.2 or 1.2 to that, I'd end up with 4.2. If I subtract 1.2 from 3, I'd end up at, what, 1.8? Okay, and those are roughly the location of the x-intercepts. I guess they wanted this as an ordered pair, so I better write it that way. So 4.2, comma 0, and 1.8, comma 0 is where I'm expecting to see that I cross the x-axis. All right, now find the xy coordinates of the y-intercept. Again, these are pretty easy. I like the y-intercept. Those are a little bit easier to calculate because you just have to plug in the value of x equals 0. It is usually a little bit easier than the process we just went through up above. We have a negative 2 plus 5 over, again, I'm going to use that vertex form that we wrote down, so 0 minus 3 squared plus 1 is what we'd have there. And so what do we end up with here? We've got a negative 2, negative 3 squared is 9, plus 1 is 10, so that's 5 over 10. Well, that's just a half, so negative 2 plus a half is a negative 1.5, right? So that would give us a y-intercept at 0, and then negative 1.5 would be our y-intercept. All right, one last thing then before we try to sketch this thing is to find the horizontal asymptote. But again, now that we've already used long division to simplify this, or actually technically they already had that in the book that way, but I'm kind of assuming that it wouldn't be so nice and give us that form. But if you look at f of x again was equal to a negative 2 plus 5 over x minus 3 squared plus 1. So again, this quotient part of this guy right here, he tells me my horizontal asymptote. So this is going to tell me then that y equals negative 2 is my horizontal asymptote. Again, I'll abbreviate that HA for horizontal asymptote. All right, there we go. We've got all our pieces that we need to come up with a sketch of this, which is really the last part of this then. Can we actually sketch what the graph of this looks like? So let's put all those pieces into this graph here. Again, there's no discontinuities. So let's mark, first of all, let me do this in a different color here. Let's mark, we came up with where the vertex of this is going to be. So let's mark that. We said that at x equals 3, y equals 3. So that was right here. Came up with where the vertex was at when we put it in vertex form. We found our x-intercepts and y-intercepts. And we said those x-intercepts were at about 1.80, so that's about right here, we'll say. And the other one was at 4.20, somewhere around there. And we also found our y-intercept. Our y-intercept was at negative 1.5, so that's about right here. And then finally we said that our horizontal asymptote was at negative 2. So we'll mark that as well. And again, if you need to mark a few more points, pick a couple more points to plug in your equation to see what it's going to look like, you could do so. But I can see that this function's got to start out above my horizontal asymptote. It's got to cross the y-axis, and then the x-axis, it's got to hit that vertex, that high point, and come back down. So it's going to look something about like this right here. That right there is a pretty accurate sketch of it. This guy right here looks a little bit different than the other ones because of the fact that we have no discontinuities. And instead what we end up with is a little vertex like this that shows up, but we still have a horizontal asymptote. All right, that is the end of this section here, part 2 of section 4-5.